Topic for today is solubility and solubility product. So, solubility product of salt. Okay, so if I say that uh, if you say that salt, how it will prepare? If you add any acid plus base, that will prepare salt plus water. So this salts can be acid, can be weak acid, strong base, or weak base, strong acid, strong base, strong acid, weak acid, weak base. So anything we can prepare the salt. Okay, so now the questions is not here. The questions now we are going to study is that if we prepare the salt is how much that is soluble, how much is soluble at a saturated solutions. So if you say that solubility of salt means at saturated state saturated state and room temperature, or at given temperature and at given temperature the solubility of, or you can say the given temperature, how much salt, let's say how much salt, let's say salt that can be dissolved in 100 gram of solution. Okay, so at 100 gram of solutions, how much that our salt is dissolved, and that should be at saturated state and given temperature, because solubility is depend on the temperature. If you increase the temperature, then the more and more amount of substances or salt will be dissolved. So at a given temperature and at a saturated state, how much the salt is dissolved to 100 gram of solutions, that is called solubility. So if I say, so the conditions is what the saturated state. What do you mean by saturated state? The saturated state we can consider as equilibrium state. Okay, so in equilibrium we understand that in equilibrium we know that if we say CH3 COH, that will dissociate into CH3 CO minus plus H plus, and we say that T equal to 0. Suppose this is C, this is 0 0, and T equal to T equilibrium, then this is C alpha, then this equal to C minus C alpha. So at equilibrium conditions, how much dissociate of C3 and CO minus. Similarly at saturated, this is for acid. Similarly for solids, for solubility, we what is says that let's say any salt, let's say V, that is in a solid forms, that will be convert into AV aqueous form. So at T equal to 0, it may be suppose C and this is 0, and at T equal to saturated state, how much, this is suppose C alpha, then C minus C alpha. So how much solubility? So for solubility, what you are taking at C alpha is taken for dissociation and the S is taken for solubility. So how much that solubility is occurred means C minus CS, sorry, CS, C minus CS. Okay, so that's what we are going to study, that how much solubility that is occur at a saturated state. Okay, so you can compare it as equilibrium. Like equilibrium we are taking like this. So at equilibrium, this is the conditions, this is the final condition which it actually really exists. We already discussed about it. So similarly, like for equilibrium, for solubility also, at saturated state it actually exists in this form. Means at this condition, this is the most stable forms, and after this part, no more solubility, no more solubility will occur. Okay, so this is the highest form of solubility at given temperature. Like this is the highest amount of dissociations at given temperature. It's highest amount of dissociation. This is similarly, this is the highest amount of solubility at given temperature. Okay, so we can compare like this. So now the questions arise that similarly, like if it says that for acids or for equilibrium, what equilibrium constant is defined only for weak electrolytes. Weak electrolytes. Let's say CH3COOH, NH4OH. So this weak electrolytes, that K equilibrium is defined. And for strong electrolytes, let's say NaOH, HCl. Here the K equilibrium is very high. So K equilibrium we generally says very high, and that is equal to value 1, very high value. So K equilibrium is not defined because it becomes very high value. So it's no useful to study the K equilibrium because it's very high value. It really tends to unity. But for weak electrolytes, this K equilibrium is defined because we will study the equilibrium constant. So we already discussed like this. So similarly for that, similarly to equilibrium, what solubility also, solubility constant is studied only for sparingly soluble salt, sparingly soluble salt or very less soluble salt. What do you mean by very less soluble salts? Like which very less amount that will dissolve. And Ksp, the solubility constant, solubility constant, let's say that is Ksp, it's not studied for highly soluble salts. Similar like strong electrolytes, K equilibrium not studied like that. Ksp is not studied for highly soluble salt. Okay, so which we will not study that which compounds have highly solubles. So we will not study the Ksp, that is highly soluble salts are like all salts of nitrates. What if the nitrates is there any salts? If nitrates is present, then they are highly soluble. So for this kinds of things, we will not study the Ksp because for this they are highly soluble. So Ksp value is very high. So we will not study that Ksp value for this. Secondly, compounds having compounds having these elements like sorry, sodium, potassium, NH4 plus, uh, cesium, rubidium. So if these compounds are there, they are highly soluble. So if these compounds are present, we will not study the Ksp value, because Ksp value going to give very high, so it's no useful to study. So for this we say that Ksp is not defined. Ksp is not defined. Okay. So next is, so which we will study mainly the sparingly soluble salt, sparingly soluble salts, that are mainly, like if we say sparingly soluble salts, it's like if we say that AgCl, AgOH, sorry, AgCl, AgI, and like the compounds of Pb, Cl2, and PbSO4. So like these compounds, they have the sparingly soluble salts, and compounds like many more. Okay, so that kinds of soluble salts are present. Let me let's say, sorry for that, PbSO4, AgI, PO4 3 minus, AgBr. So all these compounds, they can, etc. We will study the sparingly soluble salts. Okay. So let's discuss that. So let's discuss at what it means, how this solubility, is happening. So let's discuss more about it. So let's say if I draw this in this water, in this beaker, suppose water is there, and water in the solutions. Let's say if you add Pb, or you can say, let's say AgCl, let's say this AgCl. So let's say this is in solid forms. If you add to the solutions, you add to the solution, then what happened, that this will convert into, so this will some will dissolve in aqueous. So AgCl aqueous. So it's better to write down. So let's say I am adding AgCl in the solution, the AgCl that is solid in solutions I added. Then what happened, this AgCl solids, that how much it will dissolve. Let's say I have that AgCl, 2 molar concentrations of AgCl is there. So whenever I add to the solution, then what happened, that this AgCl, how much dissolve into the solutions. Okay, since this is sparingly soluble salt, so very less amounts will dissolve in the solutions. Let's say, so sparingly soluble salt, so let's say AgCl aqueous. Okay, so 2 molar is there, the very less amount will be dissolved in the salt solutions. Let's say less than 5%, less than 5% will dissolve in solution, will dissolve in solution. So like weak acids, that very less dissociate. Similarly like that, AgCl will be very less dissolve. So this is 2 molars, then let's say 0.01 molar will dissolve in the solutions. So if this is there 2 molar, then 0.01 molar of this will be dissolved in the solutions. So high amount of this molar is left in the solid form itself. Means this form is very less and this form is huge amount has left. Let's say if I take the examples, let's say when I do it, that very less amount will go and high amount is here. So let's say AgCl equals, okay, so let's say T equal to 0. If I taken that 2 molar, then this is 0.01 molar has dissolved. Means T equal to 0, so let's say it's not dissolved. At T equal to T equilibrium, let's say from here 0.1.99, then this is 0.01 molar. You see that more amount of this is present. This is at saturated state. Okay, so saturated state. So this huge amount of solid form is there, aqueous form is very less has dissolved. Okay, and what it says that this is now what it says, and this is very like strong electrolytes. Mainly this after this aqueous form of AgCl, this AgCl has 99%. This is very good electrolytes. For electrolytes, anything should come from strong electrolytes. So this AgCl comes from HCl, right? So this is strong electrolyte. So this will completely dissociate into Ag plus Ag plus Ag plus Cl minus. Yes, this is because strong electrolyte, so this is completely dissociate into Ag plus and Cl minus. So this will completely dissociate into Ag plus Cl minus. Yes. So if I say that at T equal to this is saturated solution, this amount of dissociate, then how much it is present, that will be completely dissociate. So suppose at initially this amount is present, so suppose initially this amount is present, then this is not dissociate. Okay, first you will convert this into this very less amount from this molar has dissociate. And if I say that this is T equal 0, suppose this has produced, and after some times what happens, this is completely dissociate. So T equal to T equilibrium, this is going to completely dissociate, this will become 0, and this is going to become 0.01 molar, 0.01 molar. Yes, so this is what that this is very less soluble. You understand that from 2 molars only 0.01 H soluble. So from here, but this is strong electrolyte, so this will be completely dissociate, this and this. Okay, so what is for simplifications, what you are studying that, so I can express that for simplification. See AgCl solid, if you add it to the solutions, what it will give, what will give AgCl aqueous, and this AgCl aqueous will, because this is strong electrolytes, maximum 99% this will always is to be strong electrolytes, means that it will completely dissociate. And if it mentions by itself that it is 80%, 70%, and assume that, but if not mentioned that, always assume that this is 90% dissociate. So this is going to give Ag plus Cl minus. Okay, so if at T equal to 0, let's say this is 2 molar solid is there, and let's say this is dissociate into very less concentrations. So let's say this dissociate from here to solubility 0.01 molar, then this T equal 0 not dissociate. So when T equal to T equilibrium or saturated state, what happens? This from here only very less amount to dissociate, that is how much? 0.1.99. So this is present 1.99 because this is the only less dissociated, less soluble. But this is, since this is completely dissociated, so this will dissociate into this one. This is completely used. So at T equilibrium, what we found that this aqueous form is completely used up. Okay, this aqueous form is completely used up. So at equilibrium, what things are left, which is in the solid forms and which is in ions form, that is how much dissociate this form, this ions are only present, this is not present. So whenever you studying that K equilibrium, and for solubility you write KSP. Since you are studying solubility, so for that KSP is used. So this is what concentration of product, that is Ag plus Cl minus divided by concentration reactant, but this is already used up. So we will take this value because this is already used up. So we will take Ag Cl solid, this concentration, and this is in aqueous form. So the concentrations of solid with compared to aqueous form is assumed as 1. Also this is very high value, this is very less value. So compared to this value, this is very high. So consider this is as unit 1 because this value is very high. So consider this as 1. Okay, so KSP equal to Ag plus and Cl minus. Okay, so then also there is to, like, this is very less value, so this amount of solubility is happened. So what they used to do, they simply write that, for this they used to simply write the S. So this dissociate into S and S. So this amount of solubility is happened. So they used to write that suppose this is present 2 molar, so this is S amount of solubility is happened. So at equilibrium this is totally used up and that is completely dissociate. So this S will dissociate into S and S. So this also you can write that KSP equal to S into S. So KSP equal to S square. Okay. So you understand that KSP, how actually we are related with K equilibrium. So this here the solubility of this product is very less. So from here, that since this is a strong electrolyte, so that is completely dissociated. So in books we may find that simply written that suppose AgCl is happening, AgCl solid, that is completely that is written directly like that, Ag plus Cl minus. Why they just neglect this value? Because this is K equilibrium, this is 0, so they neglect this state. So they direct let this one and this one only, this one and this one only, they neglect this value because this K equilibrium, this is 0, so it will be not taken because it is not left at equilibrium. So they neglect it and they direct write this and this. So they direct write like that, AgCl solid, Ag plus Cl minus. Okay, in the books they will write like this because at K equilibrium this value is 0. So they, so become this is not left in the solution, so we will not take. So this only left. So K equilibrium, concentration of product divided by concentration of reactants, but product is not there. So this comes from here. So we will take this one and this by this, and this is taken as unity. So KSP equal to S square. So in the books they simply write AgCl equal to S with Ag plus and Cl minus, and they will simply write, because that is K equilibrium, that is 0, so they write equal to C, T equal to 0. Suppose this is, suppose have 2 molar, then this is 0 0 and T equal to T equilibrium, so this is very less dissociate, so let's say they take as S, and since this is taken as unity, because solid is very high amount, so they write Ksp equal to S square. So they simply write like this. Okay, but it actually comes from this way. This is the actual way, but they will, for simplification, they will write like this, because K equilibrium, this value is 0. Okay, so now take one example. Suppose solubility of Pb, okay, just a minute. Solubility of, I will look the questions. PbCl2, solubility of PbCl2 is, suppose 0.279 gram per liter. Then calculate Ksp. So how will calculate this? So we know that this PbCl2 is PbCl2. This will dissociate. This is solid, and this will dissociate this into PbCl2. Sorry, PbCl2 aqueous, and this is dissociating very less, and after that this will become strong electrolyte, and that will going to be completely Pb2 plus and 2 Cl minus. Okay, and at T equal to 0, suppose this is some high amount is taken, because this is high amount, from that very less amount is dissolved. Let's say S 0 0, T equal to T equilibrium. So what happens, this is high amount is there, and this is totally dissociate, because this is strong electrolyte. So this is become, maximum times this will become strong electrolyte, and this is completely dissociate. Okay, 99%. And if it says that this amount of dissociate, then assume that value. But if not mention that, always assume that this is completely dissociate and 99% dissociate. So this is 0, this will become S. This is 1 molar, so 1 molar S, then 2 molar will be 2S. Okay, so Ksp equal to how much? Concentration of product Pb2 plus and Cl minus, and this will get power up to, and this value is assumed 1. So if I write PbCl2, because this is solid, so this is assumed 1, so I will not take it. Okay, so this value will come, and Ksp equal to Pb2 plus is how much? S, concentration S, and this is 2S, and power up to, so like this. So Ksp equal to S into power S square, that is equal to power S cube. This is the Ksp value. Okay, so now it asks to calculate the Ksp value. So S value they has given that gram per liter, but the one conditions that Ksp is always calculated in the unit of mole per liter. Okay, not gram per liter, Ksp value. And S can calculate both gram per liter and mole per liter. So our work is to convert this. So solubility is how much given? Solubility, so given solubility is 0.279 gram per liter. So we will convert into mole per liter. So you know that mole equal to how much? Mass, that is given mass by molar mass. So given mass is how much? 0.279 gram per liter, and molar mass of PbCl2. So if you calculate it, this will come 279 gram per mole. Okay, so this will going to go 279 gram per mole. So this gram cancelled up, this become 10 raised to 3. So if you take it, then this become 10 raised to minus 3. Yeah, okay, and this will go into liter, and this going to above up, then mole per liter. This is the S value. You change it into mole per liter, and Ksp equal to how much we get? 4s3. So now for S value put here 10 raised to minus 3. Okay, then that is 4 into 10 raised to how much? 3. This is minus 9. Okay, because A M sorry A M N equal to A M N. So that's what I did, right? M 3 into 3 is 9. So this is the value of Ksp, this mole per liter. Okay, so like this, if the solubility given, then we can calculate the Ksp value. Similarly, if Ksp value is given, then also we can calculate the solubility value. The relationship is this. So from this relationship, we can calculate the value. Now, the next topic is, let's study the relationship between. So we already studied the relationship between solubility and solubility product. So let's discuss the type of salts available. So types of, or you can write, this is a very good term, so relationship between solubility and solubility product. So if I search relationship between solubility and solubility product. Okay, so if I say that, then what it says that let's say AB type. AB type means like AgCl, AgI, these types will come. So let's say what is the relationship between a solubility and solubility product if AB type is there. So let's say AB. So it is fine that I will simply write like this in the shortcut, like AB, A plus and B minus, because this is actually this form AB solid, that is going to give AB equals, after that will going to give, sorry, AB A plus B minus, but I'm neglecting this and I'm down right like this. Okay, so you understand that what it actually means. So for simplifications I will write like this, then that Ksp is equal to how much, this by this, because this is huge unit, so only A plus B minus. Okay, so this if you write it, okay, so when t equal to 0, this is high amount is there, high amount is there. From here, let's say, oh, it's better to write that bonds on this. So if you say that AB, so this will dissociate into AB aqueous, okay, and this will going to dissociate into A plus B minus, okay. So when t equal to 0, let's say this is very high amount is there, then this will dissociate into, let's say, from high amount of this only less is dissociate, means let's say this is 2 molar is there, so very less amount dissociate 0, less than pi, let's say 0.01. so from here this is not dissociate, and t equal to t equilibrium, let's say this is 0.199 molar, 2 molar, okay. From 2 molar this is dissociate this amount, and so this will become what, 0, and this will become 0.01 molar, 0.01 molar, okay. So this one also we can write that, I will not write this one, so I will simply write that this is 2 molar, or let's say 1.99 molar. So let's say this is S has S amount of solubility has happened in the 0, and at equilibrium this is completely dissociated, so this is 0, this is S and S. So if write the KSP, then but this by this, so this will be S into S, so KSP equal to H square, okay. So for this type of this, the relationship between KSP and S is the H S square. Similarly, if you have the 1 raised to 2 or 2 raised to 1, for that the relationship between S and KSP is, so take that value, the examples like PbCl2, so what is it, that AB2 type, right, this is AB2 type or A2B type, so this will have, this is solid, so this will dissociate, so I'm simply writing like that, okay. You understand that how it is dissociate, right? So AB2 types dissociate into A2 plus B2B minus, okay. So now this is T equal to 0, let's, this is high amount is there, from here S amount has solubility is happened, or it's better to write that form, that is AB2 aqueous, that is going to dissociate into A2 plus 2B minus. So from T equal to 0, let's say this is high amount is there, from here S has become solubility is happened, okay, and this is 0 and T equal to T equilibrium, so this is high amount is there, high amount, this is high amount, so from here this S is completely dissociated, so this is become left 0, and this is going to become S and S. So for 1 molar S, then 2 molar, that will be 2S. So whenever you write the KSP value, K equilibrium value, that is for solubility KSP, then what, A2 plus concentrations and B minus 2 concentrations. So this concentration is S, and this is 2S and power square, okay. So KSP is S, that is equal to power square, so KSP equal to power SQ, okay. So for 1:2 is this form, and if it is A2B form also, see this become 2S, this will become 2A plus B2 minus, this will become 2S, this become 1S. So here also the same will happen, and what this will become what a plus 2 b2 minus, and this value is 2s, and since this power 2 s, so similarly for this concept ksp will come this amount, because this is 4s square into s, that is equal 4s cube. Okay, so for both the cases you will get, if 1 is to 2 or 2 is to 1, then ksp is equal to 4s cube. Okay, similarly types if that 1 is to 3 is there, like that is ALCL3 types, or you say AB3 types, then what happened, you know that ALCL3 solid that will dissociate into ALCL3 aqueous, that is going to give Al3 plus 3Cl minus, or you can general terms you can write AB3 solids, that is going to written as AB3 aqueous, that is completely dissociate, because this maximum times is strong electrolytes, that is given what A3 plus 3Cl minus. So when T equal to 0, let's say this is high amount is there, and from here there's SH solubility is happened, then this is 0 0, and when T equal to T equilibrium, this is high amount is completely dissociate, so this will become S for 1 molar, and for 3 molar it will become 3S. So KSP is A3 plus concentrations and Cl minus 3. What nonsense. This is 3B minus. Okay, so this is A3 plus and B minus Q. So this value is S, and this is 3S Q. This is S, and this is 27 SQ. Yes, that will become 27s to the power 4. So similarly we can find that the relationship between solubility and solubility product. Okay, so now the next topics is that common ion effect in solubility product. Okay, so what is the common ion effect? What will happen if you add a strong electrolyte to a, sorry, if you add a highly soluble salt to the sparingly soluble salt? Okay, both having the common ions, or both having the common ions, right? So let's say if you have AgCl, this is sparingly soluble, let's say this is solids, and let's say it is dissolved into very less AgCl aqueous, and this is completely dissociate into Ag plus Cl minus. Okay, so when T equal to 0, this is high amount is there, and this is, let's say S amount has dissolved, then this is 0 0, and T equal to T equilibrium, let's say this is high amount is there, and this is completely dissociate, because this is strong electrolytes, and strong electrolyte has the characteristics to completely dissociate. So this is 0, this is S, and this is S. Okay, so now that this is a sparingly soluble salt, to this salt, let's say if I add the NaCl, so this is highly soluble salt, that compounds having NH highly soluble, so let's say this is S, and whenever you dissolve to that solution, then this is completely soluble, completely it give NaCl. So this is high amount is there, so this also comes in a high amount, because this is high amount for sparingly soluble, very less amount is soluble, so we take as S. So but here this is highly soluble, so high amount of this H can, and this again strong electrolyte, so this completely dissociate, means Na plus Cl minus, so this also high amount is there, this also high amount is there. So if I write So if I write numerically, let's say T equal to 0, let's say this is 2 molar is there, and uh, and it will completely soluble, so this is going to give 2 molar because it is completely soluble, dissociate soluble. So this, and this is 0 0, and when T equal to T equilibrium, this is completely soluble, so this is left nothing, this is become 2 molar, and this also left nothing because that is completely dissociate, so this is become 2 molar and 2 molar. And let's say if I take this also in a numerically, let's say if I take both the cases numerically, so let's take, I take this as 2 molar, then this dissociate only very less, like 10% or less than 5%, let's say it's 0.02 molar is dissociate, dissoluble. Then T equal 0 0 and T equal to equilibrium, this is again left that 1.98 molar is still left. Okay, but here this is completely soluble, but here this sparingly soluble, so still the solid form is exist, but here solid form is not exist completely, that converted into aqueous form, so fully aqueous form is there here. But this is, since this is strong electrolytes, this also strong electrolyte, so this will completely dissociate, so again this is completely dissociate. But for this case, this is sparingly soluble, so from 2 molar, this is, let's say 0.2 molar only soluble. Okay, and since this is a strong electrolytes, so from 0.2 molar, whatever this there in equilibrium, this is completely dissociate, so this becomes 0.02 molar, 0.02 molar. So what we see is here that both the cases Cl minus is present. This is the common ion is present, but for sparingly soluble salt, this concentration is very less, because this from here very less H, very less it has dissolved, or very less aqueous forms we get. So from aqueous form, this, since this is strong electrolyte, so from here very less, since this is very less, so it also going to give very less value, because whatever it exists, that is totally converted into ions, so this amount is there in the solution, so this amount is converted because this is strong electrolyte. Okay, the problem is this is sparingly soluble salt, so from here it dissolve only very less amount. Okay, but this case, this, since this is a highly soluble, so whatever the solute is there, that is totally converted into liquid or aqueous form, and since this is strong electrolyte, so whatever is there, that is completely dissociated into ions. So in the solutions, in solution, what we got is, in solutions what we got is Ag plus we will get, Ag plus is there, Cl minus is there, Na plus is there, and AgCl solid is also there. Okay, from here, so since this Cl minus and Cl minus, they are the common ions, so what happened, if you write the Ksp below, Ksp, that is concentration of product divided by concentration of reactant, since K equilibrium is written only for sparingly soluble salt, not for highly soluble, like K equilibrium is written only for weak electrolyte, not for strong electrolyte, so I'm writing Ksp for sparingly soluble salt, so that is product by reactants, the product is Ag plus Cl minus, and product here is this value, and this is high amount is there, so compared to this is very very high, so we take it as unit 1. Why taking as unit 1? Let's say this is 0.02 value, so this value and 2 molar value, this value is very very high, so compared to this is negligible, so what you do, we want to interested in this value, so we will take this value as 1, because we are interested with this value, we are calculating with this value, so this value we take as 1. Okay, because this value is very high compared to this value. So that is AgCl solid is very high, so we take as 1, so we will not consider this value. So Ksp value is this. But now the thing is that in the solutions Ag plus is there, Cl minus is there, but Cl minus is coming from both sides, this and this. This is very high amount is there. So we will put this value is very high amount is there. So Lee-Chatter's principle what says, if concentration of product increases, then backward shifts will occur, and concentration of reactants increases, then forward shifts occur. So what happened that in solutions, what happened that this Ag plus this one, what is happening that it's getting that in these reactions Ag plus is there and Cl minus, but Cl minus, extra Cl minus is coming from here, a high value coming to this here, because these are same. So what that equation says, this equation, so that this Cl minus concentration is very high. So what happened, if the concentration of product increases, then according to Lee-Chatter's principle, it will shift the backward directions. So we already discussed that common effect, so it will shift the backward directions. So whatever this the solubility was, whatever the dissociation happening to this will decreases, although this is dissociating 0.2 molars. So this 0 to 2 molars also nearly equal to 0, because this concentration is increasing, and if concentration of product increases, then that is shift to the backward direction according to Lee-Chatter's principle. So it will shift to backward direction in this form, and this for होता मटन हाँ AgCl for 0.02 molar concentrations, again this form, again it will shift to the backward directions, because these concentrations is very so this shift to backward direction, because this concentration increases, means this concentration Hchem increases, and this concentration increases, it means shift backward direction, means the solubility of this reactions will decreases. Okay. So now if we give an examples, let's take an example. Ask to find the solubility of BS per, and Ksp value is given, suppose 10 raised to minus power molar. Okay, so ask that what is the Ksp value. First they asks in water means, and next is 0.2 molar of BaNO3 2. Okay, so we know that all nitrates are highly soluble, so we will calculate that how the solubility is affecting if that strong electrolytes will come. Okay, so this Ba is sparingly soluble salts, so let's say Ba, this is solid, so this is sparingly soluble salt, so that is going to give Bs aqueous, that is going to give Ba plus SO4 2 minus, and this is going to give Ba2 plus. Okay, now whenever T equal to 0, let's say this is very high amount is there. Okay, and from here that SH solubility is occur and 0 0 no dissociation occur and T equal to T equilibrium. Let's say this is high amount, so from here this is complete dissociate, so this will be 0 and this is going to become S and S. Okay, and let's say whenever we add the, so in water, first case, in water means normal cases. Okay, so no strong highly soluble salt is not added, so on that case Ksp equal to what, Ba 2 plus S upon 2 minus, so Ksp is equal to S into S, so Ksp equal to S square, and given that Ksp value is 10 raised to minus 4, so Ksp is 10 raised to minus 4 molar to S square, so S is equal to minus 4 by 1 by 2, that is S equal to 10 raised to minus 2 molar. Okay, now if do these reactions, what happened that I will add a strong electrolytes, that is BaNO3 now what will add, BaNO3, so this is in solid, so this is highly soluble, so this is going to give complete BaNO3 completely aqueous will come, and this will dissociate into 2Ba plus Ba2 plus NO3 2 minus. Okay, and when T equal to 0, this is high amount is there, this is also become high amount, and that is taken the 0.2 molar you have to take, so 0.2 molar, so this is also going to give 0.2 molar, so this is also going to give, because complete dissociate, yes, T equal to 0 0 0, let's say T equal to T equilibrium, so this is 0 left 0, this is going to give 0.2 molar, 0.2 molar. Okay, and since here Ba2 plus is there and here also Ba2 plus is there, so whenever you calculate the Ksp, so this is the second case, we are calculate the solubility in BaNO3, so on that case this also comes, so whenever you calculate the Ksp value, then Ksp is this amount, but Ba2 plus is also coming from here because common ions effect. Okay, so Ksp equal to S into S, but this Ba plus is coming from both sides, so 0.2 molar also added, that is S plus 0.2 molar into S, and this value is given 10 raised to minus 4 molar. Okay, so this value is very less compared to this because 0. This is very high amount. How much is there? That's completely going to give the electrolytes completely dissociate, so this value is high, so compared to this is very less, so we will take a 0.2 molar into S, that is equal to 0.4 molar. Ksp is given, so S equal to 10 raised to minus 4 into 2 into 10 raised to minus 1. So S equal to, that is going to become 10 raised to minus 3 by 2, so that is going to give 10 into 10 raised to minus 2 divided by 2, that is equal to S equal to 5 into 10 raised to minus 2 molar. So you understand that whenever you give the strong electrolytes, then See, this is the value. No, it's not. See, this concentration value is how much it given? 10 raised to minus 4 molar is there. Okay, so here if that is S square, so that is going to give 10 raised to minus 2 molar. Okay, and this amount of solubility is happening. Okay, and whenever that is given, then this S square, so this will give this S. Okay, 10 raised to minus 4 molar, that is equal to 2 into 10 raised to minus 1. So I take 10 raised to minus 3, 2. So see here the value is here. Okay, because they take the concentration very close value. So how much solubility has decreased? Here S equal to 10 raised to minus 2, that is equal to 1 into 10 raised to minus 2, and here this is 5 times. Here the S equal to 5 into 10 raised to minus 2. So this value is high value, but this value is low value has kept. Okay, so you see 5 into 10 raised to minus 2 means 5 times is decreases. Okay, so due to common I repeat, solubility is decreases by 5 times. And the last topic is, say that whenever you search any like AB solids and this dissociate into, sorry, this solubility into aqueous, after that this will going to the maximum at the strong letter, so this is going to be A plus B minus. Okay, so whenever T equal to 0, so this is high amount I taken, so let's say 0.2 molar, and this is going to give 0.01 molar, let's say, and this is 0, and whenever T equal to T anytime, then let's say 0.2 molar, let's say, and 0.9 molars and 0.01, 0.002 molars, and let's say this is going to 0.01 molar, right? 0.001 molar, then that is going to give complete dissociate 0 to 0.01 molar, 0.01 molar. And whenever T equal to T equilibrium, so it may be 0.198 molar, 0.198 molar, and this is may going to give that 0.02 molar, 0.02 molar. So we already discussed that this is at equilibrium, this is at any times. So any times we take at any times whatever the solubility is happen, that is called ionic product, and at equilibrium times what is happening, that is called solubility product. So we already discussed that what is equilibrium and what is the any time. So this is at equilibrium time, this is any time. So to this point, what is there, key, what is that, if ionic product KIP. Okay, so for this if you calculate that, for this if you calculate that K equilibrium, then we have to calculate KIP for this, then that is this by, okay, and for this if you calculate the K equilibrium, then we say KSP. Okay, so if KIP equal to KSP, then this is called solubility product. Okay, means no more soluble happen. But if it says that KIP is less than KSP, then more soluble of ions can happen. And if say that KIP is greater than KSP value, then precipitations occur. So this is very important point. So precipitations occurs when KIP is greater than KSP value. Okay, so I will solve this type of examples next class. So these are the things. If KIP is equal to KSP, then no more solubility happen. This is at saturated condition, saturated state. And if KIP is less than KSP, the KSP value is more than KIP, then we can add more solubility. We can add more ions, and there is chances of solubility happen. But if KIP is more than KSP value, then no solubility will happen. That will occur the precipitations. Okay, so today after this, thank you.